Hello, good afternoon. I am Jorge Monteiro and I'm here to talk about space debris. This is one of the last lectures in the phase 0 of the World CanSat Rocketry Championship and it will be powered by Spaceway. Spaceway, it's a company here in Portugal that aims to ignite curiosity about the space sector in all ages and aims to revolutionize the space sector, the Portuguese space sector. So here we go. So about me, a little bit about me. So I am an aerospace engineer. I finished about my master's about 2-3 years ago, and now I am an entrepreneur, and I'm also a fellow researcher for CMAST at University of Monteiro. Uh, my main tasks are connected with astrodynamics and mission analysis, and also to small sats. Um, this is my specialization. Okay, I have a lot of some international background and experience in a lot of projects around the world. So I have been national point of Portugal for the SGSC. I have been in international space uh, university in SSP 18. I have been in Samara University for the International Space Summer School for the Stuttgart University, also the Redu Center, and all of this. It's not to tell much about myself, but it's also for you to be aware of the opportunities that are around there, usually in Europe, States, and others for education in space systems, and take advantage of that, because I took advantage of that, and it's very nice education, and most of them is free. Uh, so don't be waiting for education, just go after it. Okay, and let's start about orbital space debris. But before anything else, I want you to just take some notes, take a book or a piece of paper and write, what do you think this is? And this is a picture that I took 2 years ago in the summer, I think, in 18, in exactly in the International Space University, and I was amazed by that. Okay, so before I tell you what this is, just write something, and we are going to be there in just a moment. Okay. So, summary for today. So basically, I want to divide this presentation in 5 topics, okay, all about space debris. First, I want you to understand that yes, there is junk in space, not only on Earth, but also in space. I want you to understand the environment of space debris, why space debris matters, and what can we do about it, okay? And also I will show you some mission examples that are already trying to fight the space debris, or at least are conceptual studies for doing that. Okay, so let's go. First, I want you to understand that satellite applications are now essential. I think you know that. That's why you are here watching all these lectures about the new space sector. So we need satellite applications for weather forecasting, telecommunication, navigation, television, remote sensing, security, Earth observation, lots of things. And we are increasingly reliant on space-based systems to support the technology on the ground. So it's not only that they are essential, they are increasing by a lot. Also, we have a lot of technology advancements in the last years, which allow us to do more with less. That means that small sats are here, constellations are here, they are increasing every year, and basically the miniaturization of technology allowed us to send things to space and have better performance, or at least commercialized space with that. Okay, and it's predicted that the space industry could generate revenues for more than 1 trillion by 2040. This is said by Morgan Stanley, and my opinion is that it's going to be way bigger than that, but let's see. So stuff in space. So stuff in space exists. You know that. You know that we put satellites there. But did you know that there is junk also there? So I left here a link if you want to check it out. This is the image for that link, which is stuff in dot space. So this is the all maps all the things that are currently in space right now. So it's a 3D map of objects in orbit. It's very interesting because you can click on the object and you can check what is a satellite, what is a debris, what is a rocket body. So you see that the red points are all satellites, functional satellites, while the gray ones are debris. So you see that we have a lot of debris there in lowered orbit and also some here, but most of them it's in lowered orbit. Then you have satellites here in the geostationary orbit. You can see it's perfectly noticeable, and we have rocket bodies as well in blue. So we have a lot of pieces from rockets that now are just in space. Okay, and you can check all of this in this website. It uses orbit data from spacetrack.org, and it uses a library, open source library, so you can use it, and you can click on the point and you will know the parameters, the orbital parameters, the name of a satellite or the debris. You know what is it. Okay, so just check it out. So stuff in space, as you can see here by these two very interesting graphs, stuff in space is increasing. Okay, so you go from 56 more or less when the space industry, the space industry started, and you go until 2020 now, and you see that total objects are increasing. You have two spots here that have increased a lot. We are going to talk that in a bit, but what I really want you to see is the difference between the objects. Okay, so what you see here is that most of them are fragmentation debris, so like pieces of debris that just fragmented, and they are just junk there. So we have a lot of this. Then we have spacecrafts, functional spacecrafts, still functional. Then we have mission-rated debris. This is like debris that's generated from missions. So, and then rocket bodies. Okay, and this is the total number of objects. So it's increasing. Okay, this is the number of objects and this is the mass of objects. So basically we see that in orbit we have more mass every month. That's quite obvious if we know this graph, but you see that most of the mass is spacecraft and rocket bodies, big ones, and then we have a lot of fragmentation debris that is a lot, but it's has less mass. So it's like tiny particles that are going around the Earth, and just junk. Yes, there is junk in space, as I told you. This is pollution. Okay, so you see here this graph that basically space debris is a lot. It's 28%. Space debris is defined by any defunct man-made object in space, especially in Earth orbit, because we don't have much more for that beyond that. But it's basically stuff that no longer serve a useful function. So this can be non-functional spacecraft, most of it, or fragmentation debris. Then we have the launch vehicle stage, as we saw, and mission-rated debris. But both those ones are the biggest preoccupation. Okay, and we see the evolution of space stuff in space. Okay, we see that most of the stuff are fragmentations or non-functional objects, so debris, and then only 7% are the operational spacecraft. That is quite amazing, no? So how do we track this space debris? So like how do we know that it's there, and where is it, and what can we do about it? Like, so basically we do it from the ground. That's the main. We do it mainly from the ground, so with radars and optical detectors such as lidars. They can detect debris up to 1 centimeter. It also depends on the orbits. So if we are looking in lower orbits, it's easier to find them. When we go higher orbits, it will be more difficult. But usually it's quite easy to detect this debris up to 1 centimeter, not so bigger ones. No, we can detect the bigger ones. We cannot detect the smaller ones. And what I wanted to say is that objects smaller than 10 centimeters, the smaller ones, we can detect it, but they are really unstable. So even if we know where is it in the first time, objects from 1 to 10 centimeters, most of them, they are difficult to stay in the same position or in the same orbit, and they usually are very unstable, and it's not easy to track them. Okay, so we cannot trace them. So we have two examples of radars that we use. So one is the phased radar in Cobra-Dane, and the other one is a scatter radar system from ISA. And we can see that they can track a lot of objects with this, and then we can track it from space with spacecrafts, or we can also understand what debris are there from impacts that we have. Okay, so one of these missions, or one of the most important missions in Space Force orbital debris, was Long Duration Exposure Facility by NASA, which was 69 months in space experiment that measured long-term effects of space exposure on materials. So there was a lot of different materials, and then the impacts that we had, we could take some information from how the material was affected and how much impacts we had. Okay. Also, we have these very nice diagrams called the Gabbard diagrams, which are like basically a map of debris clouds, and we map the perigee and apogee of the orbits or the fragments with respect to their orbital period. Okay, so this gives you insights about the fragments that are there, and we track them with these amazing graphs. Okay, so this, what I wanted you to understand is that there is junk in space. Okay, there is nothing that we can do about it, or maybe there is, but like it's a problem. Okay, it's a problem, and we need to characterize it, and we need to be aware of it. Okay, and let's talk about a little bit about why this is a problem, and how can we characterize this problem, and why it really going to matter. Okay, so before we go on, I wanted to tell you about a concept called Kessler syndrome. Okay, this is a very interesting concept, and this is one of the reasons why we need to be very careful with space debris. Okay, so this was a theory proposed by a NASA scientist called Donald J. Kessler in 1978, so a long time ago. Okay, this is not so present. It's a concept that is already exists for some time ago. Okay, and what it says, it basically describes a self-sustaining cascading collision of space debris in LEO. So basically, this scenario, it's a scenario where the density of the object is high enough that collisions between objects could cause a cascade in which each collision generates space debris that increases the likelihood of further collision. So a big sentence that only says that if you have space debris, you are going to have more space debris in the future. Why? Because these space debris are likely to collide with each other, and create more fragments. Okay, these fragments will then collide with each other and create more fragments, and so on. So basically, in conclusion, collisions of junk in space will eventually lead to a dangerous domino effect because of this, because every collision will generate more debris, which will generate more collisions, right? So it's simple as that. Okay, and it's a very weird phenomenon, but um, it's what we have, and it's very, and we have like some examples of that already happened. Okay, some major contribution to the population of fragments were these ones that I already told you before. So these 2 points here in the graph show you that the space debris increased a lot here, more than 30%, in 2 times, which was 2007 and 2009. Okay, 2007 was a Chinese anti-satellite test targeting the Fengyun 1C weather satellite that created more than 3,000 tracked fragments. Okay, so basically China decided to do anti-satellite tests. They were advised by NASA to not do it because it would create a lot of debris, but they wanted to do it anyway because also they told that US already did once, and it was true. They wanted to test the technology, and they did it. And basically they sent a missile to a satellite, which caused a lot of fragmentations, debris, and you see it here. And then we had in 2009 the first ever accidental collision between 2 satellites, which was Iridium 33 and Cosmos. And they are big satellites, I will show you. And this created more than 2,000 fragments, okay? And we have it in the second point. So this was 2 collisions of objects that created more fragments. That is quite obvious, no? So the first one was this one. I was already mentioning. So the first in 2007, we see that increase in total objects in space. It was big, okay, and it was in those are the orbit planes of the debris 1 month after its disintegration by the Chinese anti-missile. Okay, and what we see is that first the debris don't have the same orbital planes. This means that the debris will tend to go to other orbital planes as well, not only in the same orbit, which is really bad, and is only after 1 month. So then if we have orbital perturbations, after 1 year they will be everywhere. Okay, and then the second one was Iridium plus Cosmos. So it was an accident. The 2 satellites went one to another. We see Cosmos being here and Iridium here, and they just collide, and you see here the debris after 20 minutes and after 50 minutes. Okay, basically the Iridium have 500 kilos, the Cosmos have 900 kilos, and they were at around 800 kilometers. So you imagine that 800 kilometers, it's almost 7.5 kilometers per second. So imagine 2 objects big as them colliding with each other. It's a lot of debris. Okay, so this is just to put you on the perspective of what happens if we don't do nothing. So if we don't do nothing, what will happen is that the debris that is already in space will collide with each other, and this will create more debris, and so on. Okay, so we see here a map of the low Earth orbits, the regime where debris is more concentrated. Okay, and we have a graph from like a graph that tells you altitude by spatial density. Okay, so the number of objects by kilometer cube. Okay, so we have here the density of the objects. We see that the most of the objects, most of the debris is around 800 to 1000 kilometers, exactly where Iridium collided and where the Chinese ASA test was made. Okay, so we still have more. The density is more elevated in here because also the orbit plane is less higher, so is lower, but you see that it's in this regime. This is a very big risk of your satellite being hit by a debris. Okay. So characterizing debris. So debris can be characterized by the size and mass, okay, and where it is. Yeah? So as I was telling you, if we see this figure here, most of the debris is the density of debris is around Leo, and we see that we have different types of debris. We have debris 10 centimeters, 50 centimeters, and more than 1 meter. And we see that most of them are here and also in GEO. Okay, so this is quite normal because we have a lot of telecommunications satellites in GEO, and GEO is still one of the most used orbits. Okay, so we have a list here of the number of space debris in orbit, and in LEO it's quite usual to have these debris because first is lower orbit, is lower altitude, and they are very affected by gravitational perturbations. This is very dangerous because the collisions can occur from any direction, and the debris will spread. If there is a collision, the debris will spread by a lot of orbital planes, and impacts can occur up to 16 kilometers per second theoretically. Okay, which is twice the orbital speed. So in low Earth orbit, when we have collisions, they are very dangerous because we are going very fast, and also because the debris will be unstable in orbit and will spread around the low Earth orbits. Okay, and in high Earth orbits, we have most the geostationary and geosynchronous orbit, where we have most of the objects in space. Telecommunications, but we cannot measure accurately the debris there because it's difficult to track objects less than 1 meter there. Okay, so it's still unknown for us most of the debris that exists on high Earth orbits. Okay, and now that you understand that junk exists and where junk is and what is the type of junk that exists, why should we worry about that? So why does this matter, space debris? And just a sip of water. So I think you already have an idea why this matters and why should we worried about this, because I have already give you an hint. But let's go part by part. Okay, so first of all, that's the image that I was talking about. So what the image, what is this? So this is a hole. Okay, so nothing wrong if you answer that, it's a perfect hole. But what I wanted you to notice is this here. This is the cause of this hole. Okay, so this is a ball, a 10 millimeters aluminum sphere at 7 kilometers per second, and this is what happens. Okay, so imagine you have a satellite and there is this sphere, very small, traveling in low Earth orbit. So if it collides with your satellite, this is what happened. Okay, this is not joke. It's not a joke. So this is the first thing that I want you to understand. Hypervelocity is no joke. At low Earth orbit, we are around 7 kilometers per second, which is 25,000 kilometers per hour. So it's something that we need to really put into perspective. Okay, so any impact will cause severe damage to any space system. And here you see a simulation by NASA on with a 3mm projectile traveling at 7 kilometers per second and different materials, so different plates. This is aluminum, this is Kevlar, and this is aluminum again, with different thickness. And you see that what it does. Okay, so it creates a hole in the first one, in the second, the third one doesn't create a hole, but it put you some severe impacts and severe damage there. Okay, and if you want to check it out, the simulation, you just go to this link and you will all see. If we go for experiments, physical experiment, okay, so we have again a simulation, and how do they validate this simulation? So basically they study the impact of this sphere against the aluminum plate at a velocity of 4 kilometers per second. This is what happens in the simulation. Simulation is the experiment. So you see that the first Kevlar plate is completely penetrated, and the second one, it puts you a big hole on that. So this is what happens. Okay, so anyway, we are not so it's not so dangerous up to now. So operational spacecraft are struck by very small debris routinely with little or no effect. So it's not so dangerous as it seems for now. And also we started to use some shields that can be expensive, but they can protect spacecraft from particles up to 1 centimeters in diameter, which is already very good. And the probability of two large objects bigger than 10 centimeters in diameter colliding each other is very, very low up to now. Okay, but this can change. And if you think about the Kessler syndrome, do not forget about the Kessler syndrome. Never, when you talk about space debris, you understand that this is just what it's now, because things are evolving. Okay, and the second thing is really that one that I want you to not forget, the Kessler syndrome. Okay, so if collisions lead to more collisions and so on, so if we have collisions and if we don't do anything about this, what is going to happen is that the number of space debris will increase naturally. Okay, even if we don't do anything. So basically here the two events, the iridium and Fengun 1C breakup, they were equivalent to the number of explosion fragments expected to be generated from 50 years of spaceflight. So only 2 collisions. Okay, so basically the real problem starts when you can't control collisions anymore. So if you go up to a point where you have a lot of collisions per year, space activities will not be sustainable anymore, at least in low Earth orbits. Okay. Third reason why space debris matters, because orbital decay is limited and very slow. Okay, so basically you could ask me, what happens to junk when it returns to Earth? So it's not going to re-enter, not going to just burn in the atmosphere like everything else? Yes, it will. That's definitely. So that's the best thing about our atmosphere in terms of re-entry. So it will eliminate all the junk that exists. The problem is that orbital decay is slow. Okay, and it's only for lower orbits. So below 600 kilometers, things will normally fall back to Earth within several years, and you can see it in the graph. So if you have until 400 kilometers here, you see that you have almost 700 days until something decays. It also always depends on the object, on the on the shape of it, also on the mass. It depends on a lot of things, and also on the solar radiation, a lot of things. But this is only estimative. Okay, and you see that in low Earth orbits, yes, we can, in several years, it will decay automatically, so we don't need to worry about this. But if we go above 1,000 kilometers, if we go above 1,000 kilometers, and now I just, okay, coming back to it. If we go to 1,000 kilometers, things will not decay, okay? So we don't have enough atmosphere to be able to re-enter naturally in the atmosphere, in the Earth, okay? So we just need to, or to wait for centuries, or we need to put it propulsion, or to put the object in lowered orbits for it to re-enter, okay? And the fourth reason is uncontrolled re-entry. So it can be dangerous if you have a lot of space debris re-entering atmosphere uncontrolled, in an uncontrolled way. Why? Because first, it can be it can do damage to properties, to human lives, and everything. In general, that this doesn't occur very currently. Because why? Because we have a large ocean, we have large territories where there is no one. So usually, if things don't burn in the atmosphere, which usually occurs, and the object needs to be too big for that to not occur, it will fall in the ocean or in other region where there is no significant problem, okay? So there is no marginal risk, but even so, we need to be careful about it, because as I told you very times on this presentation, we are on a point of time where we need to start thinking about how we are going to control space debris. Okay, so in the future, this can be a serious problem. Okay, it's not so serious right now, but we need to act now. And the fifth thing is that stuff in space is increasing. We know that space is being commercialized, space is being democratized. We are here for that. We are here in this World Rocketry CanSat competition because of we want to make space stuff. So we want to launch this stuff if possible, and it's, for me, in my opinion, it's good. It's good that small satellites are rising. It's good that commercial actors are rising, that constellations will be part of our future. So we are going to have more, better communications, better Earth observation, better space activities in general. And this will help our lives. And it's predicted that it will increase a lot. But with that, space debris will also increase. Okay, so we cannot use space and not do junk, because it will be a consequence of that, and we know that from our activity on Earth. If we put more technology, if we do more stuff, we will create more junk. That's how it is. Okay, so I want you to understand that the number of space debris is likely to increase in the next decades. Okay. And we see here just one more confirmation about the constellation. So we see that small sats are rising. We see that constellations are rising in this graph. We see that most of the missions planned up to 2030 are constellations, and constellations for lower orbits, even more dangerous. Okay, this is the forecast. So we are going to have a lot of missions, and the number of debris will go up. Okay, the thing that we need to be careful is with the collisions. Collisions are really dangerous problem. what science says about this. So basically, we understand that economic and societal vulnerabilities to space hazards, in particular space debris, are growing. So we need to act now. Okay, so this is an issue today, and also as Holger Crack said, very enthusiastic is an engineer and scientists about space debris. Uh, he basically compares the problem of debris to the problem of CO2. Okay, so what he says is, if we continue operating the way we do today, we will have a disaster in 50 years. In 100 years, we don't know yet, but somehow we are going to have that disaster. And it compares quite nicely to the CO2 issue and the climate on the ground. So it's not our generation suffering from all the CO2 released into the atmosphere, it's the future generations. But it's our generation that has to take action. And the space debris problem is quite similar. So what this says is, if we don't do nothing, the next generation will have the repercussions. We are not going to be here to see it, but it's our duty to act now and to not and to do more than we did it with the CO2 issue. So we need to be aware that this problem is going to have a domino effect if we don't act, and it will be very dangerous in the future. Okay, and that's exactly what I want to talk now. So what can we do about it? So what can we do basically? So okay, it's a problem, we need to act, but how we are going to do it? It's very difficult, to be honest, because it's space. No, it's not like we can go there and just take the junk out and clean the space. Not like this. So that's why spacefaring nations are now focusing efforts on controlling the space debris environment. And there is a consensus for long-term projections about the onset of collisional cascading process in low Earth orbit. The ultimate goal, what they are doing, the nations, is to limit this runaway situation to safeguard future space operations. Okay, so they are doing mitigation actions. They have identified it and they have propagated, and they did standards based on that. We are talking about this in a bit. They also are researching about how can we active remove debris from there. Okay. But even with strict adherence to these mitigation requirements, which is not yet a safe, so it's quite difficult to put everyone accepting that they want to follow these guidelines and these requirements. It is evident that additional recommendation measures will be required in order to limit the number of objects in LEO. So mitigation requirements are not enough, and we are talking about this in a moment. Okay. So what are we doing internationally? So the first thing that we did was nations just join each other. That was so good, and it's so amazing to see that for some problems, different governments don't have the problem to just join forces and attack the problem together. And this is I hope that we do this more often in the future with other problems as well. So one thing that we did was do surveillance and tracking together. So everything that we surveil and we track and every debris that's in space is well known by all nations. So it's completely open source data. Okay. So SST, Space Surveillance and Tracking, is the monitoring and analysis of the evolution of space objects in order to issue adequate warning in case of potential threats. So basically what we do is we track the objects and we warn other nations and warn possible clients or actors about where is the space debris and where are all the objects in space, or at least the ones that we can track. And so we catalog them, we track them, and we predict their orbits. Okay, we predict in the future where they are going to be, which can be quite difficult if we are talking about very small objects that I told you that are very unstable in orbit. Okay, So we have a large network of sensors providing the most comprehensive catalog of space objects. We are going to update it to a global catalog. Okay, USA has a very good SST capabilities. Also Russia, China, and there is no here, but ESA is very good at space surveillance and tracking, and it's amazing that we are like all sharing this data, and we can cooperate together. So the three pillars for a sustainable space activity. What can we really do about space debris? Okay, and this is the three things that we can do. The first one is mitigation and prevention. So mitigation and prevention measures must be taken to minimize as possible the amount of debris created by future launches and space missions. This is basically requirements and guidelines and standards that we need to follow when we are building our spacecraft to understand and to be sure that our spacecraft will require with the guidelines and will not create debris that is unnecessary or we can remove. And we are working on that. I will talk about it. It's still in the beginning, to be honest, and we need a lot to do, but we have requirements and we have laws that tells you that you need to comply with the debris requirements. Okay, then we have active debris removal, which is basically initiatives to clear space. So basically go there and try to remove some debris that already exists, usually for larger objects, larger spacecraft that are already non-functional. So we go there and just remove it, and we are going to see how. And in orbit servicing, we can also have some similarities with active debris removal, but it's more sustainable in the terms of there are activities that want to create services in orbit. So basically to preserve the mission, the spacecraft, and to increase the orbital lifetime of the satellites, and we are going to also to check it out. Okay, so mitigation and protection, the first one. So we have an interagency of space debris coordination committee that started to really go in deep on this theme, and what we did was we produced a set of mitigation guidelines which were later adopted by the UNCOPUS, which is the UN Committee for Spaceful Uses of Outer Space. So these guidelines were basically to limit debris release during normal operations. So if we're operating in space or we are like launching a rocket, we try now to minimize the debris that it's released into space, so minimize at maximum. Then we need to minimize the potential for breakup during operations, limit the probability of accidental collisions. We can do that with orbital maneuvers, for example. We could just put some propellant on board. We refrain from intentional destruction and harmful activities, such as the anti-missile test of China. So we try to not do that anymore. Of course, there is always political issues that we need to address every time, but at least we agree that we will not do it without authorization from other parties. We need to minimize the potential for post-mission breakups resulting from stored energy and limit, this is the one most important from me, which is to limit the long-term presence of spacecraft and launch vehicle orbital stages in protected regions after the end of their missions. So basically, we have a guideline that says that every satellite put in orbit right now should comply with the 25 years post-mission rule. So basically, the orbital lifetime should be maximum 25 years. So we need to put it or in the graveyard orbit, which is an orbit for the geostationary satellites that are non-functional anymore, and we bring propulsion in the satellite, and we direct our spacecraft to the graveyard orbit if we are in geo, or we direct it to lowered orbits less than 800 kilometers, as we saw, to make sure that those satellites will re-enter on the atmosphere before 25 years. Okay, and also we started cataloging and tracing all the large size debris, and even lesser than the large size debris if we can. Okay, as I told you, is a great initiative, which is Clean Space Initiative, started in 2018, and we are going to check one mission that is particularly doing that, and what they are basically investing in is they are investing in studies about how can we reduce impacts of spacecraft or objects in space, creating regulations, assessing life cycle and orbital lifetime, what is the effects on the atmosphere of these objects, also how can we deorbit these objects, how can we design spacecrafts for in-orbit servicing, and also in specific technology innovations such as capture, rendezvous, and re-entry, how can we remove debris using these technologies. Okay, still in the mitigation and protection, here is a graph that tells you the difference with the mitigation guideline of 25 years and without it. So if we don't have the guideline of 25 years, we see the space debris going up, and here controlling the number of fragments with 90% of missions complying with the 25-year rule. Okay, so it makes a difference of 4 times. Okay, in about 100 years. So we see the difference. We see the difference. 100 years here and 200 years here. So 4 times, 2 times. Okay, so there is a difference, but it's not enough. Okay, even if we all the spacecrafts complied with these guidelines and post-mission disposals standards, mitigation measures will not be enough to fight this problem. Okay, and the problem is, even with these guidelines already done, they are not strictly implemented, and there is difficulties to legally binding actors when they launch stuff in orbit to agree and to really do these guidelines. Okay, one thing that ESA did was drama. I wanted to tell you that because I think it's a very nice software tool. Maybe you are interested on that. Which is basically a tool that allows us to estimate delta V budgets for collision avoidance, optimization of disposal strategies, estimation of orbital lifetimes, and analysis of ground casualty expectations. So it's completely free. You can download it here in this website. It allows you to comply with these guidelines of debris. Okay. Then let's go for active debris removal. So active debris removal is basically a way of removing debris from space. Okay, we can do this either by deorbiting the debris into Earth atmosphere, as I told you, or sending it to the graveyard orbit. So we talked about this, but these activities require proximity operations, and therefore it's good and it's important to invest in rendezvous technology, in capture technology, this kind of innovations. And there is different kinds of ways of doing this that are being studied. It's very difficult to do it already, but they are studying tethers, robotic arms, nets, stuff like that, that will capture the object and will bring it down to the atmosphere, okay? And we see here a graph by NASA on 2007, so a little bit old, comparing the difference of non-having active debris removal strategy and having one, okay? So we see a difference with, in long term, if we remove 5 objects per year, 10 objects per year, 20 objects per year. So we must start soon, okay, for the effects to be for us to see the effects, or the next generation see the effects of this, okay. For removing objects, it's important to understand what objects are removing, right? So this is a study of where should we focus, where are the most probable collisions to happen, and where are the targets that we should focus on. And we see that there are like 2 great areas where the probability of collision is very, very high, which is 1,000 kilometers, 82 degrees inclinations, 290 objects were identified as important targets, and sun-synchronous orbit at 800 kilometers, okay? 140 objects are identified as important targets for removal. But mostly what we want to be able to remove is objects with high mass, okay? So they often will have a big surface area which will create more fragments if something impacts there, and stuff in high collision probability, like orbits with densely populated regions and objects at high altitudes where the orbital decay is so slow that will not comply with the 25 years guideline, okay? Some missions that are already planned or done with this active debris removal. I will start with the remove debris, which was the first demonstration in history. It was done by Surrey Space Center, and it basically was a mission that used the harpoon and the net to capture an object that they released from their satellite, okay? So basically, it was launched to the ESS, then the satellite ejects a piece of space junk which then inflates as a balloon to make the target bigger than it is. Then what we do is, sorry for that, we just fire a net and we catch the debris, and then we re-enter with the space junk in Earth, okay? So we remove it from there. This was very successful. There was a lot of challenges, but it was a very, very important step for starting with the technology for removing. Then we have ESA that is planning to launch in 25 the ED orbit mission, which has the mission of removing EnviSat, which is a very big and non-functional satellite at exactly 800 kilometers altitude, so a very populated orbit, and they want to remove it from there, okay? It's one of the most dangerous objects in space that are non-functional right now. They are trying to remove it, and they are studying different possibilities. One of the possibilities is also using a net. Another one is using a robotic arm. So they were expecting to launch in 2003, but I think it got delayed, and now they just reformulated the design. They are on board doing a new mission. Okay, and then we have in-orbit servicing. So in-orbit servicing also requires proximity operations. There is basically the objective of servicing the dysfunctional satellites by refueling it, repairing it, or performing maintenance or inspection in orbit. Okay, and the aim is basically extending the lifetime of the spacecraft, which would eventually slow down the increase of space debris. So basically, if we have a non-functional spacecraft and we make it functional, it will not be debris anymore. Basically, that is the main reason. Okay, so it's very useful for geo because with active debris removal, it's difficult to bring it down to lower orbits or to make it go to the graveyard orbits. So it's very useful if we can have in-orbit servicing for geo satellites, because then we have telecommunication satellites that can go with higher orbital lifetimes, and it's a very interesting business. It's available that it's not available. It's evaluated that it reaches 3 billion over the next decade. Okay, and I tell you here in the end that it can be used as IDR as well. So how does that happen? So imagine that we put one of the options of our in-orbit services is bringing fuel to a spacecraft. When we bring fuel, one of the objectives of bringing fuel to the spacecraft can be for the spacecraft can deorbit itself. Okay, so it's basically a kind of active debris removal, because we bring the propulsion system there, we put it on a spacecraft, and the spacecraft itself will deorbit by itself. Okay, so these are the reasons why in-orbit service is a addressable market. Okay, so most is for life extension, of course, but also for deorbiting. Types of deorbiting missions or in-orbit servicing missions, sorry. The first one is OSM-1 or Restore-L from NASA. It's planned to launch this year, and it's a robotic spacecraft to refuel a live satellite. Okay, so basically it's that what I was telling you. So it will give more fuel to Landsat 7, which is already there, and we refuel it for increasing the lifetime, but also for it to have enough fuel to the orbit itself as well. Okay, and then we have O-cubed services by Airbus. This is a conceptual study yet, so it's basically Airbus. It's going after these markets, of course, and they are trying to do in-orbit servicing for geo maintenance satellites. So basically maintenance, refueling, transfer to graveyard, basically this kind of services that telecommunication satellites need, and we are going to need sooner or later if we want to increase the lifetime of our satellites. Okay, so that's the end. Okay, I hope you enjoyed it. I just wanted to give you some concluding remarks. The first one is humanity not only is polluting Earth but also space. Be aware of that. So space is getting more and more junk, and we need to address this. So not only the oceans, not only the Earth, but also space. Okay, space debris is a serious problem, and we need to address it right now, and we need practical solutions for that. Until now, active debris removal is not available. It's not technologically available. We need to invest on these solutions. We need also to invest on in-orbit servicing, and we need to do more debris guidelines and preferentially or especially to strict them more. Okay, so people need to be legal binding by these rules. So we need to make sure that everyone complies with guidelines, uh, because it's a serious problem. Okay, the most important action right now is to prevent the unnecessary creation of additional orbital debris. Is what we are doing. So try to not put more junk there. This can be done throughout prudent vehicle design and operations, and also if we clean up the environment after the orbit, and cleaning up like the orbiting. If we already bring full enough to the orbit, our spacecraft is very good, and it's the best thing that we can do right now, because cleaning up what is there remains a technical and economic challenge. Then we saw that mitigation measures alone are not sufficient. Even if we do all the mitigation measures, it's not sufficient. So we need to invest in this active debris removal and in orbit servicing, and we need to do it now. But for more investment that we can do on this, if we do this without mitigation measures, this will be useful as well, useless as well. So we need both of them. So we need active measures, active debris removal and in-orbit servicing, and passive measures, so guidelines and mitigation measures, and they need to be legal, and they need to become laws, and people need to understand that they need to comply with these rules. Okay, and this is what I have for you. I hope you enjoyed it. Thank you so much. This is my presentation, and good luck for the Water CanSat Rocket Championship, because we are going also to be there with Spaceway. Okay, thank you very much, and enjoy your afternoon. Thank you.